Most of the VR and AR headsets available today rely on the stereoscopic vision for depth cues. They usually suffer from a limited number of focal planes, which leads to divergence accommodation conflicts, which is known to be a major cause of discomfort in VR and AR. Varifocal displays and live field displays offer a wider range of focal distances. However, they both have disadvantages such as being bulky or being limited by optical diffraction. Holographic displays, on the other hand, recreate the optical waveform by modulating the amplitude and/or phase of the light, naturally addressing divergence accommodation conflicts. Additionally, holographic displays are based on optical diffraction. Smaller pixel pitch would only improve their quality. Nanophotonic phase arrays, or NPAs, are a new type of phase modulators starting to be used in holographic displays. Compared to the other commonly used liquid crystalline silicon spatial light modulators, or SLMs, the advantages of the NPAs are their integrated light source and the super-fast refresh rate. The phase modulation in our NPA is based on thermal optics. Temperature adjusts the refractive index, and therefore the phase. The modulated phase at the pixel is linear to its temperature above the ambient. This thermal modulation leads to the thermal proximity effect, where heating one pixel affects the temperature of nearby pixels. This proximity effect is modeled as a Gaussian convolution. The severity is represented by sigma. Larger sigma indicates more severe proximity effect. In our design, the sigma equals to 0.66 pixel. The effect negatively impacts the phase modulation accuracy, degrading the quality of the formed imagery. It is therefore necessary to perform the proximity effect correction, or PEC. It is also important to note that the solution must be non-negative in the correction because there is no cooling capacity. Several PEC methods for the Fourier holograms have been proposed in Song et al. 2020. The proximal PEC method, or PPEC, can achieve good correction effectiveness. However, the PPEC method uses the Fraunhofer diffraction approximation. It can be used to effectively calculate the propagation into the far field, but cannot specify the depth at which the image is shown. The Fresnel holograms use Fresnel diffraction. It is harder to compute, but can be used to propagate the waveform to a specified distance. This paper focuses on exploring the PEC methods for Fresnel holograms. We developed the Fresnel proximity effect correction method, or FPEC, by extending the PPEC method to Fresnel holograms. This method uses the proximal algorithm to find the non-negative phase x that minimizes the difference g of x between the desired image I and the intensity of the observed wavefront under the proximity effect propagated to a specified distance using Fresnel diffraction. The cost function is the sum of the intensity difference g of x and the indicator function c of x to ensure the non-negativity. For more details on the algorithm and derivation, please refer to the paper and the supplemental material. We use these parameters to specify the Fresnel propagation, including the wavelength, the size of the MPA, the pixel pitch, and the propagation distance. As a baseline to compare the FPEC method to, we adapt the IPEC method from Song et al. 2020 to the Fresnel hologram as well. We refer to this method as the iterative Fresnel PEC, or IFPEC. We show the qualitative results of the case without PEC, the IFPEC, and the FPEC methods at proximity effect level sigma equal to 0.7, 0.8, 0.9, and 1 pixel. The error masks are shown as inset in the top right. Without PEC, the image gets completely overwhelmed by noise at high proximity effect levels. The FPEC is much more efficient than the IFPEC in correcting the proximity effect and is able to restore the images close to the original. We also quantify our results with the image quality matrix SSIM and the perceptual similarity. Higher value means better image quality for both matrices. The FPEC method can effectively correct the proximity effect with sigma equal to 0.1 to 0.9 pixel, with only a slight dip at 1 pixel. As a comparison, the IFPEC method suffers from noise starting from 0.4 pixel. The two image metrics are largely consistent with each other. We can use the FPEC method and time division multiplexing to display 3D scene on the MPA. A 3D scene can be divided into a stack of 2D images at different depths. The 2D Fresnel hologram of each image can be calculated and the proximity effect corrected with the FPEC method at the desired depths. The stack of holograms can be displayed on the MPA with time division multiplexing. In this simulation, we propagate the wavefront of each hologram to an observation plane. The average of the intensities of these holograms are taken as the observation of the 3D scene. The 3D scenes are divided into over 200 slices. With 3D holograms, the user can focus on different parts of the 3D scene. We simulate this by adjusting the observation plane accordingly. There are several limitations to our method. First, the FPEC method cannot handle extremely high levels of proximity effect, such as 1 sigma equals to 1.5 or 2 pixel. Second, the processing speed of the FPEC is slow. Currently, it takes 4.28 seconds to process a 256 by 256 color image with our MATLAB implementation. However, it is still 36 times faster than the baseline IFPEC method. We believe massive parallelization and specialized hardware for FFT can dramatically accelerate the FPEC method into real time. Finally, it remains to be seen how we can correct the proximity effect on a single Fresnel hologram that encodes a 3D object. That's all of the presentation. Thank you.